Alright, still on introduction to partial derivatives. Well, maybe a higher introduction, but still introduction. You're giving z, a function of x and y, is equal to 2x to the power 3y plus cos y times y squared minus tan x. You're asked to find partial z over partial x and partial z over partial y. Now, z of x comma y is equal to 2x to the power 3y plus cos y in a bracket times y squared minus tan x. Now, partial z over partial x is equal to y squared minus tan x. So that's like v du over dx plus u dv over dx product rule. That's what I'm using. So v partial u over partial x, that's the sign here, plus u partial v, this is v partial v over partial x. Now you have y squared minus tan x. Differentiate this with respect to x. It's going to give you 6xy plus cos y. There's no excess, so this is 0. So all you have is 6x squared y plus 2 everything in the bracket. Differentiate this with respect to x. This is 0 minus differentiation of tan x is sec square x. If you check your elementary calculus, differentiation of tan is sec square, you have minus sec square x. So this is the answer for the square z over dx. Again, now for the square y, the square z over the y, you have the same symbol. You're differentiating with respect to y, so you have y squared minus tan x. Differentiate this with respect to y, this y is going out, so you have 2x to the power 3. Differentiation of cos is negative sign, so you have minus sine y plus this is coming down. Differentiate with respect to y, you just have 2y here. This is 0. So that's it for this one. Now you're given three variables. Now you're giving f of xyz is equal to sine square x minus xyz square in one bracket times x exponential xy plus 2xz. Now you're asked to find the square f over the x, the square f over the y, and the square f over the z. So we write down the function we are given. The square f over the dx is equal to the same thing. Okay, this time I use u dv over dx plus v du over dx. The same thing, same thing. So let's differentiate. We have this one, you bring it down. So we're differentiating this one now. Here, there's a product rule applied here. You have an x here as an independent variable. Then you have another x merged with with a dependent variable. So you have x times exponential xy is going to go this x and this x. That's the reason for the product rule. So this is going to be your u, this will be your v. So at a glance, what do? You see this u, this v. You know your product rule. So you say v times du dx is 1. That's the x, differential of x with respect to x is 1 plus u, which is x times dv dx. Now dv dx is also function of function. You have exponential xy. Differentiation of exponential xy is exponential xy. Differentiation of xy with respect to x is y. So you have xy exponential xy. So you have x, which is your u. Differential of dv dx is y exponential xy, y exponential xy plus. So I just want you to grab it, that you don't really need to, because there are some very lengthy work you will do in this course, and to be breaking and everything is really going to take your time. So if you can just put it in this way, it's going to be very easy for you, knowing that you have v du dx plus u dv dx, then plus differentiation of this with respect to x is 2z, plus we bring down this bracket, differentiation of this with respect to x, you have sine square x minus xyz square. Alright, so sine square x is equal to sine x square. So now d sine x square all over dx is equal to 2. Recall function of function 2, chain rule. So you have 2 sine x times differential of sine x is giving you cos x. So you have 2 sine x cos x. That's what happens here. So differential of this with respect to x is 2 sine x cos x. So in my mind, I know, like, okay, this sine x is super 2. So you have 2 sine x cos x quickly. Then minus differential of this with respect to x is yz square. So when you take off this final multiplication, you're going to be left with this as your answer. Now for differential of f with respect to y, the same thing I did here, but we are differentiating with respect to y now. So you bring down this differential of this with respect to y. This is a constant, there's no product here since y is not outside, so you have x as a constant. So differential of exponential xy is going to be x exponential xy. How? Differential of exponential xy is exponential xy. Differential of xy with respect to y is x. You have x times x exponential xy plus, you bring down this bracket too. Differentiate this related to y. There's no y here, so this is automatically 0. You have minus, differentiate this, the y is going out, so you have minus xz square. Your final answer is this. X times x is x square, x exponential xy plus this. That's it. Now for, okay, oops, I did not differentiate with respect to z. Okay, it's quite simple now. You just check it and differentiate with respect to z. I didn't differentiate, sorry, no wahala. So let's just go to the next question then. Given that z x comma y is equal to x squared plus y squared all over x plus y, find partial z over partial x comma partial z over partial y. Solution: you write down your function you're given. You look at the predominant rule. That's how I call it when I'm explaining to my friends. Predominant rule, like the major rule. There are different rules that could apply. Like this question now. Definitely, there are different rules here. There's a functional function, but the major rule that determines how you differentiate everything is the product rule. So for this one too, the major rule here is the quotient rule. And for quotient, is v du over dx minus u dv over dx all over v square. V times du over dx minus u times dv over dx. Everything is divided by v square. Right, so that's what we'll apply here very quickly. You have partial z over partial x is equal to v d over dx of u minus u d over dx of v all over v square, which should now be this. Differentiate this with respect to x, you have 2x minus u. Differentiate this with respect to x, you have 1 all over v square. When you multiply this, you have 2x squared plus 2xy minus x squared minus xy all over v square. Correlate like times 2x squared minus x squared give you x squared plus 2xy minus y squared all over v square, or xy, x plus y, everything in brackets square. Then partial z over partial y, the same thing, but we are differentiating with respect to y now. So you have this, differentiate this with respect to y, this is 0, this is 2y minus u. Differentiate this with respect to y, this is going to be 0, this is going to be 1 all over our x plus y bracket square. Open the bracket, you have 2xy plus 2y square minus x square minus y square all over x plus y, everything squared, sorry. So you have y squared plus 2xy minus x squared. When you collect like terms, this minus this will give you y squared. I don't just, since it's negative x squared, that's why you put it at the back. So you have this minus this y squared plus 2xy minus x squared all over x plus y squared. Now another question here to test is if f is equal to ln x squared plus y exponential 3x, find the f over the x and the f over the y. Solution: f is equal to ln x squared plus y exponential 3x. Now there are quite some rules here, but the major this thing we are looking at is the depending variable, which is ln. So this function of function, you have your independent variable, which is x squared plus y exponential 3x, and you have your dependent variable ln. Ln is depending on this. This can stand alone, but your ln is depending on this. So like I told you, when I differentiate function of function, I differentiate the dependent variable first, then I now differentiate the independent variable. So as I look at it at a glance, I say this is ln this. So if differentiation of this with respect to x, you differentiate it. Anything we are differentiating ln is very simple. Differentiation of d over dx of ln x is equal to 1 over x. So d over dy of ln y is equal to 1 over y. So df over dx of ln, or d ln blah 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 over dx is equals to 1 over everything, is what I'm saying. So for the ln, differentiation of this with respect to the ln now is 1 over everything attached to the ln times its function of function. Let's differentiate the independent variable with respect to x. You're going to have 2x plus, this is a constant, there's no product rule here. So the differentiation of exponential x raised to the power 3x is exponential x raised to the power 3x. Then differentiation of 3x is 3. So here you have y times exponential 3x times 3. When you multiply, you have 3y exponential 3x. Numerator times numerator, you get your final answer to be this. When you come here, the same thing with respect to y now. Differentiate ln, it is going to be 1 over everything attached to the ln times differentiation of this independent variable. This is 0. This is going to be 1, so you're left with exponential 3x. So you have times exponential 3x. You multiply and you get this. Alright, that's it for the extra examples.